Welcome to another problem session. So today we are going to talk about this thing called work. This work by a force. Okay, and we are going to discuss something that you may be already familiar with, but maybe you need some clarity. Okay, so the way the work is defined is through a line integral. So the base of definition of work is it's a number one is one number. It's going to be a positive number or negative number. So this is a scalar number. Okay, it's going to be positive or negative real number. So that's some. Second thing to notice is so if this is a path, so there's a path involved over which we need to figure out the work. Okay, so this is often not stated very directly, but you should know that. So how do you tell path? You need to know mathematics of actually telling a path. So if you have studied Calc 3 or things like that, you probably know what I could do is just give you if the object was here at time t, then at some other time it's over here. So this is like a x of t, y of t, z of t. So this locates where it is at different times. Maybe over here it is x plus dx, y plus dy, z comma z plus dz. So between here to here, you can say there is a displacement vector. This is called displacement vector. And you can say, we can write this is like a formal way of writing. But you can see from this over here that this should be dx along I hat, dy along j hat, and dz along k hat. So in Cartesian is really simple to write. Okay, so this is displacement. So if there's a force, maybe at this point when the object is in this place, there may be lots of forces. Let's look at one force. Maybe a force is of course a vector, and so this force at this point in time is point that way, and these are close enough that I can just say this same force is acting, the same force acting all through here. Okay, so this is same as that, and we'll just go with that right now. Stay with me. So if I do f dot dr, so take a dot product of displacement vector and force vector, this is the amount of work that I have to do. So this is sometimes written as like a script w, like that, delta w. So this is a work. So this is kind of like an infinitesimal work. Or you can say work on an infinitesimal path, or work on an infinitesimal path. Okay, so if I wanted to go from, okay, so this was a function of t, and r is vector at instant t, like that. So you can see I can actually do it another way. I can have f of t divide dr by dt and multiply by dt. I can do this, right? So but this stuff here is velocity. Velocity vector is dr dt. That's the definition. This is what we mean by velocity. Velocity is rate of change of the position vector, the little displacement over dt. So this is like f of t at t, velocity at t dt. Now this thing we also call it power. Okay, so this also a single number because it took a dot product. Dot product creates a single number dt. So there are several ways you can actually write the work. You can write work as power of the force. Power of the force at instant t is what was the force at instant t times velocity at instant t. All right. Now, how do you compute over a so I'm here at some point I and this some point f. So this I and f are abstract points, okay, just conceptually. And I just wrote down over here for a small work. I know what is in this little piece, okay, in that little piece. So as long as I can break it up into figure out work in all these pieces, I can add them up because they're just numbers. I can them add them up. And so work from I to F, from I to F, so this is just a symbol, should equal to work over all the sums of the delta W's, all the little pieces. Of course, this is classic definition. So this is formally, so can write formal definition will be take this integral f dot dr and go from something called I to something called f. Of course, you can go through this thing and you can say, oh, this is the same thing at ti to tf f dot v dt. You can do it like the same way, okay? So if somehow I know this, this will be dr vector. So these couple of ways of thinking about force, but what we'll find is if I go from I to F, but rather than going on this, suppose I went this way, went like that. So this was a path 1, but it went on path 2. What I will find is when you work out over here, it's actually different, often different. So WIF on path 1 is in general, sometimes it's the same. If conservative force is the same, but for when you have a friction and things like that, dissipative forces is not the same. So this is not the same as same 2 points, but on path 2. So somehow I need to actually kind of decorate all of these. This one I don't need to decorate that, but over here when I need to say do this on path, whatever path. You can do path 1 or path 2 or path 3 or path 4, whatever. You tell me path. And path will, of course, will be a function which goes on this, right? The path will be like this. So path will be x of t, y of t, z of t functions. This is called doing it by parametric way of telling you what's the path in a three-dimensional space. Okay. Okay. So this is going to be our basic definition. So this are basic definitions, and we are going to look at an example. So here's a really standard example, which is kind of made up example. So it's not a real force, and we don't see in the nature. But we're gonna do some as simple. Say I have x-axis this way and the y-axis here, and start at set O, go up to x equal to 1, turn around. So this is point A, and this is y equals to 1, and so go this way. So this is 1 0 and 0 0, and this is 1 1, and then go to point C, and then C will be 0 1, and go like this. So you can go this way. So this is path 1, and say you went from so O, A, B, C, back to O. So this is called path 1. And say instead I go to B, but I come back this way. O to A to B to O. I'm going to do path 2. So I'm going to do, so this is going to be work 1 and this is work 2. And we see after I give you the force, I'm going to compute this and show you how computation goes. Now these integrals, there are names for these integrals because this depends on, this is describes path. So this is called path integral. Or some in math books, you call it line integral. So whichever you use is up to you. So this is line integral. How to do line integrals is not that difficult, but you got to make sure that you have a vector this and use the property of the path that you're on. So let's look at force. Force we're going to do is maybe x square I hat plus xy j hat. Okay, so we're going to do this force. Okay, so you can see on this part x is 0. So on this path, no matter where you are, force, let's call it 1 2 3 4, f on 4, f on 4 is just 0 because x equal to 0, and f on 1, y equal to 0. So f on 1 will be y equal to 0. So this is not there. So this is just x square I had. F on 2 is x equal to 1. That's the path. On this path, you don't use the direction when you're trying to figure out what force is on what segment. So on this segment, f on 2, this vector will be x equal to 1. So this will be 1 and this will be 1. This will be I hat plus y j hat. And f on 3, what do you think f on 3 will be? On this you have y equals to, this one is y equals to 1. So y equals to 1 will be here. So x square I hat plus x j hat. X square I hat plus x j hat. So those are the forces on different things. So now it's very easy. Let's work this out, and then we're going to work this out later. Okay. So let's see. So let's see on 1. So W1, W on path 1, path 2 is W1 plus W2 plus W3 plus W4. So those are 4 guys. And we're going to call this guy 5. And we're going to do, this will just be W1 plus W2 plus W5. Okay. All right, so is that okay? That's everything clear? All right, so on 1, W1 is going to be F dot dr on 1, on path 1. Path 1, it has y equal to 0 and x goes from 0 to 1. I go from 0 to, that's where the direction comes in. The direction is here, not over here. And the dr is always going to be in dx I hat plus dy j hat. If you're third dimension, you get dz k hat. But we don't have third dimension here, just have two dimension here. So if you look at f1, it's x square I hat. So I hat with I hat will give me 1, but I hat with j hat will give me 0. So this is going to be y equal to 0, x equal to 0 to 1, and it's going to be x square I hat dot dx I hat plus x I hat plus d dot dy j hat, and this is 0 because I hat dot j hat is 0, and this is just going to be 0 to 1. This integral I'm going to write this way, x square dx, and it's going to be 1/3. Okay. All right. Yeah, got any questions? I hope not. All right, so let's do the, on path 2, I already figured out what the force is, and this is both I hat and j hat. So this is, and y goes from 0 to 1. So x equal to 1 on this path, and y goes from 0 to 1, and I have makes it using this, if I hat plus y j hat dotted into, now on this the dr with x equal to 1, this just means dx equal to 0. That's just j hat dy. That's what that is. So j hat dy. Okay. If dx x equal to 1, that means hit d on both sides, d1 is 0. That's how it's 0, okay? Because it's constant, this will have to be 0. X is not changing, only y is changing. And so this actually is silent, and this just becomes, in the y variable goes from 0 to 1. That's the direction, I go from 0 to 1. And y dy, and that just becomes half. All right, that's good. Very good. So number 3, let's do number 3. Number 3, W3 is this path, which is y equals to 1, and x goes from now 1 to 0. So this is path directions from 1 to 0. And and x square I hat plus x j hat, so those are the force dot, and over here y is not changing, so just I hat times dx, and so this with this will give me 0, and this with this give me 1. So this just becomes, in the 1 go 1 to 0, x squared dx should be minus 1/3. And the 4, W4, we already know the force here is 0 because y is 0, x is 0, and x, the way we took the force, yeah, we did this our force. When x is 0, this goes to 0, and this goes to 0. So when force is 0, so this is 0. So we figured out W1. I just have to add these 4 segments. So W on path 1 is just W on segment 1, W on segment 2, W on segment 3, W on segment 4, and just 1/3 plus half minus 1/3 plus 0, and this is just half. Good. Now let's work out this. So instead of going from here, we go this way, then I return through this diagonal path. Okay, the diagonal, we just think of this as a line. So there's a relationship between y and x on this one. So we need to just, for this, we already know this guy, or this knows. So we figured out 1 and 2, and now to figure out 5. On 5, and this is 1, 1, and this is 0, 0. These 2 points tell me y equals just x. On path 5, that's the case. So dy is dx. So I can write everything in terms of dx or dy. So let's write everything in dx. So the f, just x square, this I hat dx plus j hat x squared dy, because x equal to dx also. So I had x squared dx. Well, don't need to do more than that. You can't add these guys. This is not equal to 2x squared dx, something like that. Not like that. If you want to get x squared dx common, you'll get I hat plus j hat. Okay. Now dr is I hat dx plus j hat dy, and dy is dx. So this is also dx I hat dx plus j hat dx. So you can take dx and I hat plus j hat. I'll take a dot product of these two guys. F dot dr. What will I get? I will get this is I kind of messed up here. There's no dx here, no dx here, no dx here. Okay, so f is just x squared and xy became x squared. Okay, so this is going to be x squared dx I hat plus j hat dot I hat plus j hat. So if you open this up, you have I hat dot I hat, which will be 1, I hat dot j hat from here, this guy, and then this guy. This will become a 0, plus this time this j hat dot I hat, this go to 0, plus j hat dot j hat, this is 1. So now it's actually 2x squared dx. This is 1 and this is 1. So that's how it becomes 2x squared dx. So, I mean, you might have guessed this, good for you, but sometimes, it just numerically it worked out. It doesn't have to be that way all the time. So now I need to integrate this x integral. So I need to go from x equal to 1 to x equal to 0. X equal to 1, x equal to 0. So 1 to 0, x equal to 1 to x equal to 0, 2x squared dx. So you have a 2x cubed over 3, 1 to 0, so minus 2/3. So w on path 2 is w1 plus w2 plus w5, right? And w1, w2, I know we worked this out earlier. It's going to be 1/3, and w2 is a half. 1/3 plus half minus 2/3. Let's see. So you can already see I can make it. Oh, this is like half minus 1/3. So we have a 6. 3 minus 2 is 1/6. So W on path 1 was half, which is not equal to W on path 2, which is 1/6. So this is one case where that happens to be different. You really have to just work it out. Now, if I'll let you in on it, that if you have a force that can be written as, del of a potential function, if you can write like this, what is del? Del is I hat d dx plus j hat d dy plus k hat d dz. If that's the case, meaning if there was a v for that force, if it was written like f was written, this minus is just a convention, okay? If a is equal to minus I hat d dx v minus j hat dv dy minus k hat dv dz, if this thing exists, then it will be totally path independent. You can actually integrate it. So let me show you formally how it can be. So W I to F F dot dr. Now I to F minus del V dot dr. Now this is nothing but dV. In 3-dimensional dV is just that. If you don't know how I got that dV, which is a function of x, y, z, then it will be dV dx dx. So this must change along the x, dV dy, this by in direction of dy plus dV dz dz. And you can write this as dV dx I hat plus dV dy j hat plus dV dz k hat I hat dx dot product dx plus j hat dy plus k hat dz, right? So this whole thing is minus f dot dr. And so that's how it's dv. So now it's just very simple. V is just a normal function, just a normal variable. So this is equal to minus I f dv, and that's going to be just integrated very nicely. V I to f, so V at I minus V at f. And this is how the concept of potential energy comes from. That if a force is, you can write it like this, then it's called conservative force. And in the case of conservative force, you will be just totally independent of path. So this work for conservative forces will be independent of path, and that is a very fundamental reason, and that has to do with force. Actually, there is a potential, a function, this is called potential. I can find a function whose gradient, so this is called gradient of V, whose gradient is the force itself. In that case, it will be independent of path. If I can't find something like that, or it doesn't exist, if no function exists whose gradient will be f, then in that case you will have path dependence. So if you go back to the one that we worked, we worked on this force a little bit earlier. Yeah, we worked on this force. This force is not minus del v of any v, and that's what path it is path dependent. Okay, so for an example will be like the gravity is a spring force. A spring force will be a path independent, right? So let's look at spring forces minus I hat kx, just along the x-axis. All right, then this would be you can actually find half kx square, and if you do a del of this with a minus here, this, if you work it out, is going to be that thing, like minus I hat d dx of half kx square minus j hat d dx and did ky square minus k hat d dy d dz half kx square, my x square. X and y independent, so this will be 0. X and z are independent, this will be 0. So this, take a derivative here and you have minus k I hat kx. So that's why this is the corresponding potential energy corresponding to the force this. All right, okay. So that's a little bit advanced, but gives you a better perspectives and how to use it and not get tripped up. Okay. Now there are cases in which you can do work integral. It's called work integral. You can do it if path is given parametrically. Okay, so one of the great examples is this, say, pendulum. So if you, now let's do a pendulum this side. So if you do it some theta 0 and theta 1, so how much work will be done by gravity? Gravity is mg. How much work will be done by gravity when it goes from this position to this position on this path? So you can if you kind of do it like this is x-axis and this is y-axis, then these angles will be the polar coordinates. You could do it in polar coordinate, right? And this mg, force of gravity, will be just minus, no, actually plus mg, because x is down here, I hat. And if you look at little path here, this path will be dr. Dr will be along, if this is from the x, this will be the theta hat direction, right? The polar theta hat direction will be like that. And if this is length L, then, and this angle is, say, d theta, so L d theta will be the size of this, and the direction will be theta hat, not minus theta hat, although I will use the direction later. What's the theta hat? Theta is, if this is at angle theta, that's going to be minus sine theta I hat plus cosine theta j hat. I can try to remember this. You can make sure that theta hat dot theta hat is 1. You can check that out. And if you do fg dot dr, that's going to be with this it's going to be mg sine theta d theta. And if I integrate from, say, this is initial is this and final is this third one, so that's going to be integrate from theta 0 to theta 1 mg cosine theta 0 to theta 1. This just turns out to minus mg sine theta integrated should be plus here, right? Mg theta 1 cosine theta 1 cosine theta 2. This sine theta will integrated eats up this minus sign, absorbs that minus sign. So this should be equal to this should be equal to minus change in potential energy U1 minus U0. So the U is actually minus mg cosine theta here. Mg, there's L somewhere. There's L somewhere. There's L, 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 L. So this is the formula for potential energy function. Of course, you can any formula of minus mg L cosine theta plus a constant will help. It will be the same thing, right? Because all that matters is taking the derivative of this equals to that. All right. So this is normally when we do problems in this, we kind of say, okay, this is the lowest point. I'm going to call this zero potential energy. Then when it's over here, is potential energy is this whole thing is L, and this much is L cosine theta 0. So this is L minus L cosine theta 0, this height. And over here it will be L cosine theta 1. So L minus L cosine theta 1. So we kind of add up a little bit in these things. Normally when you use this as a 0, it's going to be mgl plus add up like this. But this is just a constant. Makes no difference in the physics. What we have done when we did this, if you trace it back, and I will encourage you to trace it back, I picked this as my 0 of the potential energy. So anything below that was a negative, anything above was positive. So this is a negative amount at any angle theta, and so it has this much negative potential energy, and that's why it was just mgl cosine theta with a minus sign here, because minus, if potential energy is 0 at this level, anything will be negative below that, anything above that will be positive. All right, so I think that's a good review of how to calculate work using different parts and how it relates to potential energy itself, and a little bit of advanced math just to get you motivated to do this. Just a reminder that I've been trying to post as maybe very frequently, very regularly now. So if you subscribe, that I appreciate that. And if you have subscribed, great job. And you can tell your friends, and then maybe tell your teachers. Maybe hit a like button if you like this kind of detailed discussion of physics problems. Okay, so I will see you in the next video. Bye.